Now we are ready to move to the spectral method. This is the main method that we learn in this semester, and it's the main one that we learned in Chapter 5 for Laplace's equation. And we're going to see that applying the method is going to turn out the same. So here's the heat equation, and look, this time we're looking at equals F. So this is a non-homogeneous PDE, and what's nice about the spectral method is that this will work for non-homogeneous PDE, and we still also have non-homogeneous initial condition. The initial condition has a G that's non-zero, and the PDE has an equals F that is non-zero, so doubly non-homogeneous, and that's okay. The spectral method is to apply that Fourier's trick by taking both sides of the equation, multiplying by this eigenfunction that we already found in the last method, the sine of n pi over Lx. We already know that those are the eigenfunctions of that negative second derivative operator with respect to x. So we multiply by the eigenfunction and integrate from 0 to L. And so when we do that, we can split that into every single term. Now here on this whiteboard, I have emphasized that a minus kappa uxx is the same as a plus kappa, and I put the minus in there because this is the negative second derivative operator. The reason we like the spectral method is because minus second derivative operator, we know exactly what those eigenfunctions are. Those eigenfunctions are or the eigenvalue problem says that negative LU, or LU, is lambda U. We can take the operator and replace it with the eigenvalues. So doing L of U, where L is negative second derivative, doing L of U is the same as doing lambda times U. And so I know you can't read this in here. This is on the handout. Here, I'm emphasizing that on this term, the one with the t derivative, since the eigenfunction does not depend on t, x and t are independent, the derivative with respect to t can come outside the integral. And so follow on your handout on that page with the integrals in that equation. The first one is the time derivative, like the time derivative comes out. These are exactly the Fourier coefficients of u. These are also exactly the Fourier coefficients of u. And the last one is exactly the Fourier coefficients of f. So by doing this Fourier's trick, we were able to get rid of the second derivative operator by replacing it with its eigenvalues. Like the operation is the same as scalar multiplication, since we've solved that eigenvalue problem. And then all these integrals are exactly the Fourier coefficient integrals. And so we can write this not in terms of solving for u, but we can write it in terms of solving for un, all of the Fourier coefficients. And so these Fourier coefficients, they do depend on t. There's a u of xt in there and an f of xt. And there is still this time derivative, but using Fourier's trick, or the spectral method, that just took care of x. Took care of x. This equation has no more x in it. This is an equation just with t in it. This is not a partial differential equation anymore. The x derivatives were taken care of by the spectral method, so this is now an ODE in t, in the time variable t. We know how to solve this. This is a first order ODE linear constant coefficients. We can divide everything by row C, and then we would have exactly the same type of equation that we had just a few videos ago in the separation of variables. And so I trust that you could play that video if you don't remember how to solve a first order linear ODE. There will be an integrating factor involved, just like on test 1 of last semester in chapter 2 of that textbook. An integrating factor involved there will be lots of constants in that integrating factor. You'll integrate from t0 to t, and so when you integrate, you'll get not the constants times t, but the constants times t minus t0. And notice, unlike the one in the video before, this is non-homogeneous, and really that's okay. We don't ever do anything to this. We just keep track of it. So you'll have to, instead of multiplying 0 on this side with the integrating factor and getting 0, that's why on the equation on the handout, where there's the integral with the fn of s in it, that fn of s is multiplied by the exponential e to the positive, all those constants, times s. Notice that minus sign distributes, and so that's really like to the e to the positive s times all those constants. That's from the integrating factor. And then it's at the end when you divide by the integrating factor that gives e to the minus t. And notice that e to the minus t shows up in both terms of the solution, the term that depends on the initial conditions and the term that has the f in it. So then the final thing to notice is that when, and this is on the solution equation on your handout, when t equals t0, that's at the initial condition, when you plug in t0 for t, the exponentials become 1, because e to the 0 is 1, and the integral becomes 0, because the integral from t0 to t0 is 0. And so you should find that when t equals t0, a lot of pieces of that formula cancel or go away, and you're left with then exactly the initial conditions of the Fourier initial conditions of u are the Fourier coefficients gn of that initial condition.